that, and then we're going to go just on repeat.
So
We're in 15 minutes.
today, we're going to look at a very important application of derivatives. It is called optimization. So that's the handout I just gave you. As always, it's also on the website for the class. Again, it's another kind of word problem kind of thing that's happening here. But related rates, again, there's a sequence of steps that you always follow. You basically do this in the same order, and it will be able to solve any optimization problem that we have in this class. So, in short, to optimize something means to make it as good as it can possibly be, right? You want to find the optimum solution. And it turns out that in many ways, in many contexts, that idea of making something as good as it can be, turns out you can formulate that problem into making something as large as it can possibly be, or as small as it can possibly be. Right? So if you're talking about, for example, profits, I want profits to be high. I want to create a situation where my profit is the maximum profit I can get. If we're talking about cost, then I would want that to be low. I would want a situation where my costs are as low as they can possibly get, and so on and so forth. So a lot of times this idea of the best situation, you can think about it in terms of making something as big as possible or as small as possible. Or in other words, finding the maximum of something or the minimum of something. And calculus can help us with that. And so we're going to apply calculus to help us do that. There's one other thing though, is in reality, there are always limits, there are always constraints on the amount of things you can do, right? Your profit will never be infinity because you always have a limit to how much you can do, right? You can only hire so many workers to make your products and sell your products, right? You don't have an infinite amount of people working for you. And even so, you don't have an infinite amount of customers to sell things to, for example. There's always a limit in there, and so there's always a restriction. And so the optimization system, which you can order now, the optimization system takes this into account. So it talks about making something as large as possible or as small as possible within a certain constraint that the situation will impose on you. So you will have some sort of limit as to what you can do, but within those limits you want to make something as large or as small as possible in order to cultivate the best possible situation. And that kind of brings us to an optimization standpoint. So again, step one, we're going to have a sequence of steps here. Again, it's 6 steps. Step 1, read the problem carefully. Step 2, just like in related rates, you're usually going to want to draw a diagram if one is not given, just to sort of get a handle on the situation. And step 3, we do have to come up with equations here, but there are 2 kinds of equations that we have to come up with for an optimization problem. So it's a little bit more difficult than related rates because you have to come up with 2 equations, not just one. So one equation is called your constraint equation, and that's going to be the equation that describes the restriction that you have. Right? So whatever you have limits on, come up with an equation to describe that limit. That's called your constraint equation. And then you'll have the objective equation, and this is the equation that describes the thing you want to maximize or minimize. It's your objective to make this thing as big or as large, as small as possible. Right? Step 4, always the same thing. You're going to solve for one variable in your constraint and plug it into the objective. Turns out the objective will always have too many variables to deal with. So the constraint equation will have less variables. You'll be able to solve for something in the constraint, plug it into the objective to get the objective into one variable. And that's when you can start to do calculus. Now you want to find the absolute maximum and minimum of the objective function. Right? And it will have the constraint built into it because we solved for something in the constraint and we plugged it into the objective. So that constraint is now built into the problem itself. So now when we find the max or min of that, it's taken into account that the constraint is true. And so we can find the maximum or minimum of that. One thing here, it says theoretically we are after the absolute max and min, but very usually the endpoints won't solve the problem. So you'd really look for the local max or mins here, but there are very few cases in which it does solve the problem. So you should be responsible and check the endpoints anyway. But it's very rarely a solution, and I'm not really going to give you a problem if that's a solution anyway. But there are a few. There might be a problem in your homework where that's the case. And at the end of the day, you need to 6, answer the question. So the question is going to ask you for something very specific. Make sure you give them that specific thing that they asked for instead of some other random fact that might be related or not. And that's basically it. So the calculus really happens in step 5 when we're finding the absolute max and min, which we know how to do since last time. And so really steps 1 through 4 is where the meat of the problem is going to be. It's the setup. And a lot of times, just as with related rates, the geometry of the situation is going to give us a lot of information. So I think problem 1, we're going to jump to the examples. Problem 1 is actually is a relatively easy example. I think it illustrates the steps very well. So we're going to go through the steps with problem 1, so you can see it in action, and then you can answer any questions you might have after going through example 1, and then we'll do a few more examples that are more complicated and more like what you might see on the test. So, we're doing optimization. I forgot what section this is, but it's optimization. 4.6. And we're going to do example 1 from the handout. Again, if you lose it, it's on the website. So, step 1, we're going to read very carefully to understand the situation. We have to, 1, recognize it's an optimization problem, and 2, recognize the important pieces of information that will allow us to get through the next few steps. So it says a farmer has 100 feet of fencing, which is to make a rectangular enclosure. If he wants the enclosure to encompass the maximum possible area that he can plant the maximum number of crops in, what should the dimensions of the enclosure be? Okay. So you'll notice some things here. It talks about the maximum possible thing. You might even remember this problem. It's very similar to the llama problem that was on one of the reviews, where I built that rectangular fence in the backyard. I want to make the area as large as possible. We didn't need calculus there, but we're going to use calculus here, even though we could avoid it technically here. So he wants to make a rectangular enclosure the maximum amount possible. What is the limit here? What is the restraint, the constraint? Yeah?
The 100 feet.
The 100 feet of fencing. He doesn't have an infinite amount of fencing. If you wanted to have the largest possible area, get an infinitely long fence and just fence around the whole world, and then the whole world. Right, there's a limit here. He only has 100 feet to get this done. And then you can realize that there are many possibilities here. You could do something like, make this 20 feet and 20 feet and 30 and 30. Or you could do something like 10 and 10, and then this would be 40 and 40. You could do something like 25 by 25, right? There are many possibilities here. You want to find the best possibility. Okay. So instead of trial and error, have this guy build a bunch of fences, measure the area, and then pull it down and build another fence. Right? There's a method here that we can actually know what the best possible scenario is. And that's going to be the optimization scenario. So we realize that we want to maximize area, so we know it's an optimization problem, because that's usually talking about maximizing or minimizing something. And so now 2, we're going to come up with a diagram that represents our situation. We know he wants to make a rectangular enclosure, so a rectangle is the best diagram to use here. Now at the moment, I don't know what the dimensions are. In fact, did we ask for the dimensions? Yeah, in fact, they asked us for the dimensions, which means I don't know what length and width he should build it at. So let's call these variables x and y. So now our goal is to figure out what is x and what is y to have the maximum amount of area. That brings us to step 3. Step 3, you're going to set up 2 equations. One is going to be the constraint equation. And one is going to be the objective equation. The constraint equation describes the restriction. We know that the restriction here, amount of fencing. Right? And another thing you can get from reading the problem is the constraint is usually the guy that you're given the value for, right? They didn't tell you the area, we don't know the area, but they told you exactly how much fence we have. We have 100 feet. So it's usually going to be the thing that you're given the value for, okay? So the restriction is the amount of fencing. So how can I describe with this situation the amount of fencing?
2x plus 2y equals 100.
Exactly. The amount of fencing is the distance around this shape that I just drew. So the amount of fencing is a perimeter equation. In other words, 2x plus 2y is going to be 100. Or I can divide it by 2, my x plus y must be equal to 50. Right? And this is my constraint equation. This is the equation based on this diagram and the situation they just described. This describes the restriction that I have. The length plus the width must add up to 50. Now what's the objective? Yeah?
Is it x times y equals a?
Right, it's the area equation. He wants to make the area as large as possible. The objective is to maximize area. Right? So the area equation is going to describe the objective. So here, again, it's a rectangle, so we actually know how to find area. Area is going to be length times width, so it's going to be x times y. That's your objective equation. Which brings us to step 4. Plug constraint into objective. So what you're going to do is you're going to solve for one of the variables here. In general, it doesn't matter who you solve for, but depending on the formula, it might be more convenient to solve for one as opposed to the other. In this case, I don't really see. This is just x times y, it's pretty symmetric. This is also pretty symmetric. So let's just solve for y. But a similar thing would happen if I solve for x. So I can solve for y here, and what I'm going to do is I'm going to plug it in there. Right? So notice my objective equation has 2 variables. We don't know multivariable calculus, we only know single variable calculus, so to deal with 2 variables is not something we know how to do. So we want to get it in terms of 1 variable, so we use a constraint, plug it in there, and so we have the new objective now is x times 50 minus x. So this is now my area function in terms of one of the variables. Any questions so far? So now I have this function. Now yes, I realize that this is a parabola, it's upside down, we can find the vertex, but remember that that only would work because it's a quadratic. We want to keep things more general here, so let's actually use calculus to get to the maximum point. This brings us to, I can just simplify this a little bit. This is 50x minus x squared. Brings us to step 5. Now we're going to maximize area. Which means we need to find the critical points. So we need to set a prime equal to 0. This means, what's the derivative of this?
50 minus 2x.
50 minus 2x is equal to 0. This means x equals 25 is a critical point. So now, I want a different color. Couple issues here. Well, not issues, just some things you can take away from this. One, you're in a question, there's only one critical point. Odds are that's going to be the guy that's going to solve your solution, because who else is there to choose from? Right? But technically, at this point, we could have gotten several x values, and we have to do a test. So in general, you are going to want to test the critical point. Right, so you're gonna, like we were doing before when we were doing curve sketching, we're gonna put 25 here. Of course it can't be below 0 because it's a length, and it can go all the way up to 100. But we're gonna test this in A prime. I can plug in a random number in this interval, say 1. Plug in a random number over this interval, say 26. Notice that if I plug that into this, if I plug in 1 for x, this would be positive, which means the function is increasing. If I plug in 26 for x, this would be negative, the function is decreasing, and so that actually means that this is the maximum. Okay. So in general, you have to test it here, you kind of would just run with the 25. Also in general, you would check the endpoints. Right? You should at least consider them, make sure that they aren't a possible solution. And you know the endpoints for the x, what's the most amount you can possibly devote to one side of this fence? Well, nothing or 100. And clearly either of those cases, neither work because you would have 0 area, right? If you put all 100 to the length, there's nothing left for the width. So you wouldn't have a rectangular fence. If you put nothing for the length, then you, again, wouldn't have any fence. So the endpoints clearly do not solve the situation, right? That means you didn't actually build a rectangle in the first place, right? But it is something you should consider, right? There are very few cases where this will actually solve the situation. So in general, to be good calculus students, we would test these things, but you get to a point where there's only one. That's got to be the answer. So that being said, we're going to run with this point. That's the critical point. So now we can, so we realize here that x equals 25 maximizes area. Which brings us to step 6. Now we're going to answer the question. Now what did the question ask?
What should the dimensions be?
The dimensions, which means you haven't answered the question unless you tell them the dimensions of the fence, which means you need to tell them what is the length and what is the width.
Give me 5 each.
Right, so the length here was x, and that was 25, and I believe our units were feet. The width is the y, but we solved for the y. The y was actually 50 minus x, and so that is also 25. So this means it's a 25 by 25 foot enclosure. Right? But it's important that you actually answer them what they asked for. You need to end this question with the dimensions. It is possible that instead of asking for the dimensions, they ask you what is the maximum area, in which case you wouldn't solve for x and y, you don't solve for a, and the answer would be a equals 25 squared, right? And in that case, you could just take this 25, plug it into the a equation, right? Because we had over here that a was equal to 50x minus x squared. So if someone asks you for, was that it? 50x minus x squared? Yeah. So if instead they ask you for the area, what you would have done is you would have just taken this x value, plug it in here, and give that as the answer, right? So it's very important in step 6 that you specifically give them what it is they asked you for. And that's basically it. That's optimization in a nutshell. So again, very standard strategy, very standard order. Literally the only thing that changes is the diagram that you will have, and hence the 2 equations that you set up. But you follow the same sequence of steps to solve any problem. If there are no questions, we'll move on to some more examples. Let's go in order. Let's try example 2. A rectangular corral of 162 square meters is to be fenced off and then divided by a fence into two sections as shown in the figure to the right. So they gave you a diagram.
That's number 3.
Sorry. Design an open rectangular box. Forgot how to count. We're in calculus. Design an open rectangular box with square ends having a volume of 36 cubic inches that minimizes the amount of material required for construction. So here, we want to minimize the amount of material used because we want to save the earth and all that. And so, we want to create a box. So, step 1, we're going to read. Notice that we want to construct a box out of some material that minimizes the amount of material used, which 2 brings us to the diagram. So here, we have an open box. Now what do they tell us about this box? It has square ends. So, how would I label this box?
Length, width, and height. X, Y, and Z.
X.
2 of them are the same.
2 of them are the same because it's a square.
Wow.
So the right side must be a square, which would force the left side to be a square. And what about this part?
Y.
That we don't know, right? So we know about the left and the right ends need to be a square. No specific information was given about the width of the other one. So I call that a different variable. Again, you want to minimize the amount of variables used. So you have X, Y, and Z. There are 3 variables to worry about. That's too much information. So you really read to see if you can eliminate some of this information. And we're told that one side is the one end is square. So that gives us this diagram. 3. So we need a constraint and the objective. What's our constraint?
36 cubic inches.
Right, volume equals 36. As usual, the constraint is the guy where they tell you exactly how much you have. Right? The box must contain 36 cubic feet. So the volume is our constraint. Now we know that, can you come up with an equation for the volume of this box? Yeah.
X squared equals 36.
Yeah, length times width times height, you get x squared times y. So we know that x squared times y equals 36. That's my constraint equation. What is the objective?
Minimize the amount of material.
Okay, how can I describe that, the amount of material?
Surface area.
Surface area. We want to minimize surface area. So the area equation, the surface area of this box, is going to be my objective equation. And so how can I do that here? What's the surface area of this box?
2x squared.
Okay, sum of the area is all the faces, so the right side, the area is x squared, the left side, the area is x squared, so there we have 2x squares. This is for the left and right side. Plus.
xy.
So I have x times y, and the base is x times y.
Oh,
So-
there's no top to it.
So it's 3xy, because there is no top again, yes? It's an open box, so there's no top. So there are only 3 other sides, right? So the other 3 sides. So that becomes my surface area equation for this box. That's my objective equation. You'll notice that it has several variables in it. You don't know how to deal with that, so we want to get into a single variable. So we move on to step 4. Plug constraint into objective. So now we have a choice of things to solve for. Who would you rather solve for? I'd rather solve for y because, to solve for x, you'll get a square root. Sure, we don't have to worry about pluses and minuses, but square roots are annoying to deal with anyway. So in this case, it doesn't matter who you solve for, but I would rather solve for the y because it's much easier. So I get that y is equal to 36 over x squared. Don't have to worry about any square roots. And so this means I can plug that into my new area function. So I have 2x squared plus 3x times the y. I'm going to plug this in. 36 over x squared. So that means my area will be 2x squared plus this, cancel that. So that's 3 times 36 over x. So now this is my area equation in one variable. So now, don't really have space over there. Let's go over here. Now let's move on to step 5. We want to minimize area, which means we're going to need to find the critical points for the area function and find the derivative, find the maximum, the minimum point in this case. So it's very important. Again, step 1, you need to read so you know what you're looking for. Is it a maximum or a minimum? And so here, we're going to find a prime that is equal to 4x. What's the derivative of this?
Negative 108 over x squared.
Alright, so you can bring this up, think of it as x to the minus 1, do the power rule. So you have negative x to the minus 2. That gives you this. So now you're finding critical points. And so you're going to set this guy equal to 0. Or undefined. This means, how would I solve this?
You pull 4 out.
Sure.
We should also pull X out.
I have an x and a, yeah?
You multiply both sides by x squared.
Multiply by x squared, yeah, taking it all the way back to lecture 1. Right, you have an equation with fractions, you multiply the equation by the LCD. And so this would give you 4x cubed minus 108 equals 0. And so basically you would get x cubed equals 108 divided by 4.
20,
That goes to what?
27.
That goes into 27. So this means that you take x as the cube root of 27. So it's, of course, undefined would mean x equals 0, but of course we reject this because that means we don't actually have a box. Which kind of means you also reject endpoints. So in one shot we're going to reject it. This is the only guy of concern to us. Because the endpoints would give us 0 and we wouldn't have a box. So now let's run with that. So again, 3, 0. You can pick a number here, pick a number here. It's going to give you that. So this means x equals 3 equals inches minimizes 8. And that brings us to step 6. So they asked us for something specific, so let's give them design. So I guess you can just tell them the length, width, and the height of the box. Length, width, height. So my x is 3. This implies that my y is
4.
what was it? It was 36 over x squared. So that was
36 over 9.
36 over 9. So the box, the design for the box that will have the desired constraint as well as the minimum amount of surface area is you want a 3 by 3 by 4 box. 3 inches by 3 inches by 4 inches would be a box that has a volume of exactly 36, but it uses the smallest amount of area possible for a box of that volume size. So another example. Let's jump to 5. Because cost is often something that we'll be asked about. So the manager of a department store wants to build a 600 square foot rectangular enclosure in the store's parking lot to display some equipment. 3 sides of the enclosure is built from redwood fencing, and it costs him $14 per foot of fencing. The 4th side is built of cement blocks. That's going to cost him $28 for each foot on that side. Find the dimensions of the enclosure that will minimize the cost of the building materials for the enclosure. So here, this guy wants to build some sort of display enclosure. He already knows how he wants to make it. 3 sides is going to be a wood fencing, 1 side is going to be brick fencing, and he figures out the cost for each. So now what he wants to do is minimize the cost. How can he build this fence? What dimensions of the enclosure should he build so that it's as cheap as possible, but at the same time, it should be able to hold 600 square feet of stuff. Coming up to example 5. Step 1, read. Step 2, diagram. Sort of figure out this situation, what's going on here. So we know it's a rectangular enclosure. 1 side is different from the other 3 sides. One of these sides is not like the others. So let's say that's the brick wall, right? Just for argument's sake. Again, x, y. So that describes the situation. Now, purple or blue shows up. Purple. Now, if I were to talk about cost here, right? Let's actually label the cost on this diagram. What would the cost of this length be?
14x.
14x.
Wait, it's 28x. Oh no. Okay.
This is 14x would be the cost. It's $14. That's what it said, right? $14 per running foot for these 3 sides of the redwood fencing. There are x feet here. It's $14 times the amount of feet. This part here, again, would cost 14 times the number of feet. This part here would be 14 times the number of feet. This part here
28x.
would be 28 times the number of feet.
Why wouldn't it have a different variable?
Yeah.
Like, or is it just because the price?
It's just 'cause
Different
of my
variable
size.
where?
I don't know why. It's like it's a different.
It's just because the length is the same.
Because it's like a different. It's brick. I would think it would be different.
Oh, you're talking about this side?
Yeah.
Yeah, it's because of what was described. We know 3 sides of the fence is by redwood. So these are wood fencing. This is actually a brick wall on that 3rd side. the wood fencing costs $14 per running foot, so if we have Y feet, the cost is going to be 14Y. We have Y feet over here, the cost is 14Y. We have X feet over here, it's 14X. The brick wall costs $28 per running foot, and so that's 28X.
So the variable is the same, it's just like the rate.
They're the same
It's
length.
the same dimension.
It's
both
yeah, it's
dimension
just
and
the
price.
length is what I'm talking about. And again, we weren't told in the beginning that it's a square, that's why we have to use X and Y. We don't know what the dimension should be, what is the length, what is the width. So I have two variables here that describes the length of the width and the length and the width respectively, and then I'm looking at the cost of each side because the cost is the important thing here. So now if we move on to 3, we're talking about constraint and the objective. So what is the constraint here?
2y plus x 600. Wait, just kidding.
Prices.
What?
It's 600 square feet
600 square feet. So what does that refer to?
area.
Area. Constraint is the area. Area is equal to 600 square feet. So you can't build as big as you want. He only has 600 square feet of his parking lot that he can devote to this. And so the area is going to be, well, so our diagram is a rectangle, so we know the area is just x times y. And the objective is we want to, what do we want to do up here?
Minimize cost.
Want to minimize cost. So the cost equation is going to be important. Let's call that C. And the cost is just going to be the sum of the cost for each side of this fence. So I'm just going to add these guys all up. So that's going to be 14x plus 28x plus 14y plus 14y. And so this would mean that my cost is, what's 14 plus 28?
42.
Answer the light, universe and everything. And then this would be 28y. 4. Put the constraint into the objective. So I can solve for one variable here, plug it in there. Who would you rather solve for?
Y.
Okay. So here we see that y is equal to 600 divided by x, which means I can plug that in over here. So this means that cost is equal to 42x plus 28 times 600. And now we want to minimize that. Minimize C. Notice that the endpoints don't work. Again, you'd have, if your x is 0, then you don't have a fence. Endpoints don't work. So you try to find the local max and mins. So we're going to find C prime. It's going to be 42 minus 28 minus 600 over x squared. If I set C prime equal to 0, set I have 42 minus 28 600 over x squared equals 0. You can multiply both sides by x squared. So I have x squared is equal to, well, x would be the square root of 28 600 over 42. Does that work out to something nice?
Are you supposed to multiply the 28 times 600 by 2?
By what?
Oh no, wait. Never mind.
It's only over an x, so a negative 1 comes down, and so that's okay.
Why is it minus? 42 minus.
Because this here is 28 times 600. I bring the x up, think of it as x to the minus 1, do the power rule, so the negative 1 comes down, subtract 1 from the power. This is a nice number.
It's 20.
It's 20, exactly? Yeah. Okay, nice. So x equals 20 seems to work here. And again, I mean, a formality, but you can just plop in your 20, try 21, and try 1, and you'll see that's. So basically, we need x equals 20 feet to minimize cost. And what was the question? It says, find the dimensions. So just say the length and the width. Yeah.
Wasn't it plus 28 times 600? Wasn't it 42 plus that? I thought it was.
Yeah, but we did the derivative. This is the derivative.
Oh, okay, yeah.
Yeah, with the negative complement. C prime. So we needed x to be 20 feet to minimize cost. So I would say, I don't remember the diagram, I called this x. So this is x equals 20, which means that our y would be, was 600 divided by 20. So that's 30. So this would mean the dimensions are 20 by 30, 20 feet by 30 feet, with the brick being, the brick wall being 20 feet, and build a wall. That's the best wall to build. It's a fantastic wall, the best wall. 20 feet is the best length for a wall. Yeah?
With why don't you also move the x squared to the other side? Like you just put it to
At this point?
Yeah.
Oh, because there's a fraction. I multiplied both sides by x squared. So 0 times x squared is 0. X squared times this, the x squared is cancel, and then I have 42 times x squared gives me this. I just multiply by the LCM to kill all the fractions. So now I have this equation. Then I move that over, and then divide by 42 and take the square root. Technically it's plus or minus. X is a length, so it can't be negative, so I ignore the negative. And so, yeah, 20 does it. And x was the length of the one side that was brick was length x. So it's a 20 by 30 foot enclosure. So this, you'll see that it has 600 square feet of area, and the brick wall is one of the 20 foot sides. Do you guys want another example, or do you think you got it? Huh? You want another example?
Yeah. Yep. Yep.
What happens if we don't do another page?
We'd finish the next section in the next 15 minutes.
Let's do
That's
all
what he's
examples.
thinking. That's why I was like, definitely another example. Because if we say we got it, he's definitely going to move on to the next section. I know this guy.
Let's just do the rest of that.
Wait, are we finishing?
We already sort of know how to do it. I mean, this is just for variety, so you can see a variety of problems. Let's do problem 4 and get out of here. People trying to slow me down. Okay, so problem 4. A cylindrical can without a top is to be made to hold 8,000 pi cubic meters of liquid. Find the dimensions of the can that will minimize the amount of material needed to make the can. That is, minimize the surface area of the can. So step 1, optimization. We know we want to minimize something, so we know it's an optimization problem. 2, they described it as a cylindrical can. So the dimensions of a can are really the radius and the height. Give anyone those 2 pieces of information, they can know exactly how large the can is. So that's our diagram here. 3, constraint equation and objective equation. What's the constraint? Volume. Know that volume must be 8,000 pi. What's the volume of this object? Is there a closed can? It's a can without a top, so there's no top. Okay, so right, so we look at this forward. The area of the base times the height. So it's pi r squared h equals 8,000 pi, which in other words means r squared h is equal to 8,000 because it divides both sides by pi. Objective, want to minimize area. So here we're going to deal with how would I find the surface area of this can?
Pi r squared plus 2r pi h.
Yes, that is correct.
Hey,
So you get like 2 extra points on the next quiz. Yay! I'm kidding. There are no more quizzes.
yes.
So now you didn't
Yes,
get it.
you missed it.
Can I still have
We have
those
all
minutes?
Not
Okay, so the area, what you realize is there's a base that has radius r. So we realize that the area is the area of the base plus the area of the side. So the idea is to figure out the area of the side. What you can kind of do is you can kind of slice this can down and then open it, and you'll end up with a rectangle. You realize that the height of this rectangle is h, but what is the distance that when you unfold it, the distance is just the distance around the circumference. So that's just 2 pi r. And so now the area is going to be pi r squared plus 2 pi r h. And so, yeah, now we're moving on to step 4. Plug constraint into objective. And so I can solve for either one here. In this case, I choose to solve for the h, so I won't have to deal with like a radical or anything. So my h is going to be 8,000 divided by r squared, which means I'm going to go over here, I'm going to plug that in. My a is going to be pi r squared plus 2 pi r times 8,000 over r squared. R's will cancel, so this is really r to the minus 1, so when I'm differentiating it, I can use the power rule. So now we're at step 5. We want to minimize area. Then a quick concept check. Realize that the endpoint of the work the minimum amount of radius I can choose is r equals 0, and the height is r equals 0, h equals 0, up to h equals 1,000, but endpoint doesn't work. And so we move on to find a prime, which is going to be 2 pi r. And we're finding it with respect to r, so there's nothing to worry about here. Minus 2 pi times 8,000 r to the minus 2. Set a prime equals 0, and so this means that 2 pi r minus 2 pi times 8,000 over r squared is equal to 0. I can divide both sides by 2 pi and then multiply the entire equation by r squared, and this would give me here r cubed minus 8,000 equals 0. So again, my r is going to be the cube root of 8,000. And what's that, 20? And so now we get to step 6. We want to minimize specifically by telling them the dimensions, which means you need the radius. So here we need dimensions of the can, which means we need the radius and the height. We know that r is equal to 20. This would mean that the height was, I think it was 8,000 over r squared.
Yeah.
That's 8,000 over 20 squared. That's 400. That's also 20. So dimensions to minimize area is r equals 20 and the height equals 20. You have a question?
It's concerning the announcement
What
that was
announcement?
made when I was in the bathroom.
Make an announcement. What are you talking about?
Okay, because I heard that one, you're giving all the tests, all the quizzes on one day. Two,
Yeah, one day, let's back to back. I gotta give you guys 5 quizzes. Why would I?
did you guys plan this? Because multiple people said that to me.
So obviously why?
It was soy boy. That's what he said. Hey, let's all agree to tell her that. Yeah. All right. I'll see you guys on Friday. Oh, and we finished optimization, so we'll do the homework for this. Yeah.
So you walked away with all the figure out of that.
You walked in, right, it was homework.
We decided to.
And you guys
Sure, because the entrance is always going to be like 0 is the one it gets.
Are we getting it homework?
We need to write endpoints don't work.
Yeah, at least write this to make sure I know that you thought about it. But clearly, if you have some physical object and one thing is 0, the object doesn't exist.
So the only thing that's due is, oh, hi.